We are still working on alternating series. I thought I'd do one more alternating series just to, get into the swing of things. And then I'll finish with a very specific question. 13 and 14 are the only two examples of it, where they ask you to estimate what a converging alternating series would add up to I think it's 4 decimal places. And so I'll show you how you can go about that. But first we'll do a pretty standard alternating series one. Try to find something that's pretty standard. Yeah, this one. I don't know if I've done this one. They all start looking the same after a while. It's got the standard look at least. I don't recollect if we've done that one, but that's fine. Okay, alternating series, pretty obvious to recognize, right? This thing here. Let's check the limit as n tends to infinity and see if it is in fact 0, because that's the first hurdle it needs to do. Now, in some questions, you just have to do it by, mathematical intuition. It's obvious that the thing's going to be 0 or something. In the same way that sometimes you have to say it's decreasing because it's kind of obvious that it's decreasing. But if you can do it formally, you should. There's only really one method to find this limit. And what would that method be, looking at what we have here?
L'Hospital.
Yeah, has to be that guy. So I'm going to do the limit as n tends to infinity. If you differentiate a natural log, you get that. If you differentiate 5n, you get that. You probably don't need this line, but I'll put it in anyway. That's what that simplifies down to. And we can do brute force. And bingo, that's a good start, right? It's not a guarantee that it's going to converge, but it's a good start. Don't we now have to prove it's decreasing? So I'm going to take the real valued function. And sometimes you just have to say intuitively it's obvious it's decreasing. But if it's possible, and this is, you should prove it. And the way that we prove it is by showing that the derivative is negative. In this particular question, that's going to be my f, and this is going to be my g. And I hope it just by looking at it, that you can see it has to be a quotient rule. Agreed? Fraction, quotient rule. Let's see what we get here. If you differentiate this guy, you get 1 over x times this guy, which is 5x. Take away, leave this guy alone, and a 5. And on the bottom, you get that guy squared, which I'm just going to do in my head, which is 5x times itself is this guy. Let's see what it simplifies down to. Looks like I get 5, take away 5 log x over 25x squared. Now, provided x is technically greater than or equal to 1, but you can get away with a number like 10. Would you agree if x is big enough, won't 5 take away 5 log x eventually be negative? Now, even if it means you have to get to 1 billion, won't it eventually be negative forever? Does that seem reasonable? That this top will be a negative number if x is big enough. And would you agree that 25x squared is positive all the time? Therefore, it's negative. And the derivative is negative, so it's decreasing. And we have a series whose limit is 0 and it's decreasing, and that alternating series then converges. And for all that hard work, all that I will see is a little dot on converges. And in other questions, a little dot on diverges. But there's a lot of work involved in doing that, especially when you do your test question. So that's a pretty standard, no frills, alternating series test question. Okay. Now, the last piece of this section that we need to do is we need to cover a question that looks something like this. Estimate the value of this alternating series, and we'll assume that it converges, so I won't bother to prove that. And we're going to do it to 4 decimal places. So we know it converges. We'd like to know what it converges to, right? What's its answer? Now, if it was a geometric series, the answer would be A over 1 minus R, and that would be a perfect answer. If I wanted to do an estimate to an accuracy 4 decimal places, it's not as obvious how I'm going to go about that. So let me tell you a little trick. And it says this. If you have an alternating series that converges, the error in using n terms is n plus 1, the next term. So what does that mean? Well, do you know if I just did n equals 1 to 3, you would agree that would be an estimate, right? Because I'm not using all the terms, I'm just using the first 3, right? According to that, the error, right, the maximum you can be out is basically, oops, forget that guy, is basically 4 squared over e to the 4. And let's see what that looks like. That's 16 divided by e to the power of 4. And the answer is about 0.3. So whatever answer I get, and I'm just making this up because I don't want to do it, it takes too long, but can imagine it adds up to 12.5. What I can now say is that the real answer is 12.5, give or take 0.3. Do you see we have a little tolerance now? Now, if I had done not 3, but 30 terms, this fella here would change. It would become 30 squared over e to the power of 30. And that's huge. Well, not huge, extremely small, is what I meant to say.
Wouldn't it be 31?
Thank you. It would be 31. So let's just pretend that it added up to that, right? If you did 31, it'd be 31 squared e to 31. Because when you use 30 terms, the next term, the one you didn't use, is basically the error. So 31 squared divided by e to the power of 31. I want to get a really ridiculous answer. Right. Do you see that weird answer that you get? I'll just call it 3.3 e to the negative 11. That means 3.3 times 10 to the negative 11. That's pretty much good to 10 decimal places. You know that number means 0.00033, right? Tons of zeros. So this series is good to 10 decimal places if I used 30 terms. So that's the process that we're going to use to answer the question, Let's find the estimate of an alternating series correct to 4 decimal places. So let me actually do an example. Oops, excuse me. From the homework. So here's our first one. It's like question 11. This is the converging alternating series. And we want this estimate to be good to 4 decimal places. So I have to adapt what we talked about here. Because I worked backwards. I went and said, okay, if I use 4 terms, what's my error? If I use 5 terms, what's my error? If I use 6 terms, what's my error? Right? Now, I certainly could do that. How many terms do you think you would need to get 4 decimal places the accuracy? Just give me a guess. Don't guess 4 million. Guess a little number.
15.
Ooh. Now, if you use 15, won't 1 over 6 to the power of 15 times 15 funny guy called factorial, won't that be our error? And I just said 15, didn't I? I caught myself this time. Isn't it 16 that you use? Now, if you go to your calculator and you try and do that guy, you're going to have fun, but I'll do it. I'll try and do it. 1 divided by 6 to the power of 16 times 16. Uh-oh, factorial. I've not done one of them in my calculator before. I don't know where to get it. Let me show you where to get it. Hit the math button. Scroll over to the end, and it's choice number 4. You see a little factorial? Boom. That's how you get factorial, right? It's kind of hidden, but it's in there. Brackets. Whoa. Would you agree that this answer is, oh, that's good to about 25 decimal places. So 15 is far too many. Do you know one of those games that you might have played when you were younger where I'm thinking of a number or I've written it down on a piece of paper and you guess and I say it's too big and then you have another guess and it's too small and eventually you get the thing? We're playing that game right now. Well, that's too much, right? Too accurate. I only want 4 decimal places. So give me a smaller number than 15.
4.
I hear 4 and I hear 2. I'm going to do 4. And let's see what the error looks like in 4. It's going to be 1 over 6 to the power of 5, 6 factorial. 1 divided by, remember the brackets, 6 to the power of 5 times 6.
Are you sure that's a 6 factorial?
I'm glad people are paying attention today because I am screwing up everywhere. Told you today was a weird day. 6 to the power of 5, 5 factorial, boom. Oh, that's about 1 times e to the negative 6. That's actually 5 decimal places. So still a little bit too accurate, right? If you want 4 decimal places, you basically want that guy to be e to the negative 5, just to be sure. So would it seem reasonable that 3 might be the guess to use? Let's try it out. 1 over 6 to the 4, 4 factorial. 1 divided by bracket 6 to the power of 4 times 4 factorial. Hey, we got it. Anything with an e to the negative 5 is probably going to be good to 4 decimal places. So you might say, well, what have we found here? We have found that if you want this answer correct to four decimal places, you only need to use 3 terms. So to finish this question off, I'm going to calculate what is called in the math world the partial sum. Partial sum means you're only partially adding it up. In this case, 1 to 3. So it's going to be negative 1 to the 1, 6 to the 1, 1 factorial, negative 1 squared, 6 factorial, 6 to the power of 2, 2 factorial, plus negative 1 cubed over 6 to the power of 3 times 3 factorial. And this guy, and that is a 1. This guy is negative 0.16667. This guy is plus, what on earth is it equal to? 1 divided by, put a bracket around it, 6 squared times 2 factorial is 0.013 few eighths. This guy is negative, and if you do 1 divided by 6 cubed times 3 factorial, you get 0.00077. And this guy here is wrong. Let me do him again. He's 1 divided by brackets 6 squared times 2 factorial. There we go. This guy is 0.013, and I take it back. It was right. I thought I'd done them wrong. So I take all of those guys up and I combine them, and whatever the answer is, we are finished. So what you do is you take this formula and you guess. Now, you don't need to guess big. I'll tell you right now, all the answers are between 1 and 6. So you don't have a lot of guessing, right? So you find out you need 3 terms or 2 terms or 4 terms, that kind of number. And how do you know that? Well, if you use 3 terms, don't you use the guy with 4? And that's the error. If you use 2 terms and so on, you will eventually get an answer with an e to the negative 5. That's basically 0.0000 and something, and that's going to be good to 4 decimal places because of that. So that's the guy you're looking for, an e to the negative 5, so you can get 4 decimal places. In this particular question, you only needed, what, 3 ugly guys? Yeah, it's messy and it's time consuming, but it is plug and chug as well. Are we good with that process?
So is the answer the addition of those 3 terms?
Yeah. So your answer is what these 3 things add up to. And you will make sure that when you do it, whatever these 3 things add up to, you remember to round them off to 4 decimal places, because that's what the question was at the beginning, right? Give me an estimate to 4. Now, you might write them a few more extra terms because you feel like it. As long as you make sure that you round off to 4, that's going to be safe. Are we good? Because I'd like to move on, because these things take forever and a day if I need to do another one. Are we good? Now, you notice how unalgebraic it is, isn't it? Kind of weird in math to guess. It's basically guess and check. You think, oh, I'll use 4 terms. What would the error look like? Too much, right? Too much. I'll use 3. Just got it right. Oh, by the way, if let's say we did a question and 6 was too accurate, but 4 wasn't accurate enough, I wouldn't need to do 5. Wouldn't it kind of have to be 5 because there's only 1 number left? So I guess you could save your workload just a tiny bit. Right. It's not going to save you a great deal of time, but that's the best I can do for you.
Is it ever not a whole number?
It has to be a whole number, because in a series you can only add up 1, 2, or 3 terms. So you're trying to find out, is it 1 term I use? Is it 3 terms that I use? Is it 4 terms? So it has to be a whole number. You won't really be able to generally solve these, at least the hard ones. Can you see that there isn't an algebraic way of, for what value of n does this equal 0.0005, right? That's why we had to do the guessing game. As long as you don't mind guessing. Do you know what Murphy's Law is? If there's 6 numbers to guess, it's always the last one, isn't it? Right? And do you know the lucky buggers amongst you? The first one you guess is actually the one, and you don't need to look anymore. Right? So, have fun. So, it's time to start our next topic, in fact, our last topic. And it is a last topic for the test. Oh, excuse me, I have to do something. To open another window up. That's not the one. To show you what kind of awkward day I had today, in my previous class, I had tons of windows open. So I hit the wrong button and I closed every single window, which wasn't a good idea because it meant I had to go back and open all the ones that I shouldn't have closed. So you can't kind of see what I've got, but I'll give you a quick idea. Right in front of me is my main screen, and to the left of me is my smaller screen. The main screen, I get to see all your happy faces, and that way I've got a feedback on, yeah, this is working or it's not, and I can tell who's talking when you speak. And then on my side screen, I tend to do, in this case, I've got up the next section so I can look at some of their questions and write them down. And when I go to the whiteboard, all your guys move over to the little baby screen, and I see my whiteboard in front of me because it takes up one of my screens. So if you ever watch me and you think his head is moving an awful lot, it's because I'm looking at one of the 2 monitors depending on what I need to do at any given moment. So right now, I'm going to go into the white screen. Oh, I may actually be on the white screen. Right. So we are going to show you a new test. It is called the ratio test. And that's what I'm going to focus on today. And the ratio test is section 11.6. I'm going to first just basically tell you how the ratio test works. Suppose you have a general series, right? Nothing, it doesn't need to look like anything particular. Most of the time, it tends to be fractions, but that's just the way it is, right? But any series at all. What you do in the ratio test is you find the limit as n tends to infinity of the ratio of the next term in the sequence, right, over its previous term. And that ratio, that limit of this ratio, and it's an absolute value to make sure it's positive, we'll call it L. And what the ratio test says, it says if this L is greater than 1, then the series diverges. And if it is less than 1, the series converges. And if it's equal to 1, it's inconclusive. Which is just another way of saying we don't know. We don't know if it converges, we don't know if it diverges. This isn't the test that makes it happen. It would be really nice if it was a perfect, right? If this is true, it converges. If that is true, it diverges. Because quite a lot of the other tests, isn't that correct? I mean, if I just off the top of my head, if you're doing the geometric series test, if the absolute value of the common ratio is less than 1, it converges, and if it's greater than or equal to 1, it diverges, right? It is or it isn't. Would you agree in the alternating series it either is or it isn't, right? It converges or it doesn't. There isn't this don't know. Unless they give you in your options converge, diverge, or inconclusive, right? Unless it gives you those 3 options, I think it's pretty safe bet it's going to be one of these 2. Now, to be able to do this funny ratio limit thing, let me get you some practice at just finding an plus 1. Suppose an was that guy. An plus 1 is basically what you get when you take each n and replace it by n plus 1. So you would get n plus 1 squared, e to the n plus 1 natural log of n plus 1. Does that kind of make sense now? When somebody says, okay, what does this an plus 1, what is it? Well, if an is this, that's what an plus 1 would be. Suppose an was 2n plus 1 over n cubed, right? Could happen. Then won't an plus 1 be 2 lots of n plus 1, add 1, over n plus 1 cubed? But sometimes you can tidy up the thing. You can do a little style point on it. In this case here, I wouldn't do anything. I just leave that alone. But in this case here, would you agree that's slightly nicer looking than that? Do you feel comfortable now about what an an plus 1 would be? Let's do one with a factorial then, just to finish. Suppose you had 5 to the n plus 1 over n factorial. Let's figure out what a to the n plus 1 would be. Well, I'll do the easy one first, right? The n would just become n plus 1 factorial. What would 5 to the n plus 1 look like if you replace the n with an n plus 1?
Would it be n plus 1 and then plus 1?
Yeah. Which we would probably simplify out as n plus 2. Okay, from most of the happy faces, I'm saying, I think we're good at that. Would we be good at that? You're going to see them lots and lots of times, so it's not like it's going to disappear. Next thing I want to show you is how to cancel things with powers and how to cancel things that have factorials. Because in a lot of these questions, you can imagine that you're going to have a fraction, right? Pretty much guaranteed. And something in the top is probably going to cancel with some on the bottom, right? It's going to simplify in some way. So suppose you had that, right? Good harm. Now, if these share a common base, aren't you allowed to simplify that down? Agreed? Basically, the top guy divided by the bottom. Now, if you want to write it out in its formal way, don't you take the top power and subtract the bottom power? That ends up being a rather ugly -2, but that becomes 1 over 5 squared. And there is nothing wrong in doing that because it is correct. But I tend to do it slightly differently, and it's a bit of a shortcut. the top power and the bottom power are having a fight. The one that wins the fight is the biggest. Would you agree that 2n plus 3 is bigger than 2n plus 1? And so the one that wins goes on the bottom. And the one that loses gets a 1. Now, how much did it win by is the power that we write here. So 2n plus 1 on the top, 2n plus 3 on the bottom. How much does the bottom win by?
2.
And essentially, is it not just a shortcut way of doing what I did earlier? Right. Try another one of these. E to the n plus 7 over e to the n plus 3. Okay, the e's are having a battle. Does the e on the top win or does the e on the bottom win?
The top.
How much does he win by?
4.
And e to the 4 over 1, which is basically e to the 4. I just find that a convenience, right? A helpful, because you're going to do a lot of these cancelling and you don't want to have to do, 3 or 4 lines just to find out that it's 1 over 5 squared. It's easy to get kind of lost in the process if you have to do that. So this is my, there's a fight going on between the top and the bottom argument. And I think it works quite well. Now, let's look at how factorials behave. Because they behave in a different way. Suppose I had n factorial on the top and n plus 1 factorial on the bottom, which is very likely to happen. That's quite a common one to get. You want to simplify this guy down. I want you to imagine how you would write n factorial if it was a number. Wouldn't you just go 1 times 2 times 3 until you got to the last number n? And then underneath it, 1 plus n plus 1 factorial. Now, when you got to the end, it would be n plus 1. Agreed? What would be the number just before the n plus 1?
N.
N. Now, if you do it like this, you will find that factorials play well together. They cancel out a lot. Cancel, 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 cancel. Do you see that there's only an n plus 1 left on the top and you always leave behind a 1? So that's what that one would be. This divided by this just becomes a 1 over n plus 1. Let's try something a bit harder. 2n plus 1 factorial over 2n plus 3 factorial. That could happen. So it's going to be 1 times 2 times 3, and it'll finish at 2n plus 1. And it's going to be 1 times 2 times 3, and it's going to finish at 2n plus 3. Now, to do this cancelling thing, take the biggest factorial and keep working backwards until it matches up with the top one, right? The smaller one. Now, this is 2n plus 3. The one just before it would be called 2n plus 2, agreed? And the one just before that would be 2n plus 1. Do you see I've now met up with the top guy? And now you can basically cancel all of these guys out. And in this case, that's what would be left behind. Okay, so factorial's a little bit different. The way that you simplify, the way you cancel. I'll give you one to try. Okay, you got 1 minute. Simplify that guy. Here goes. 2n plus 2 is the bigger one, so imagine that going. 2n factorial would be 1.222, and it finish at 2n, right? Since this is larger, it will finish there. If you work backwards, it's there. If you work backwards, it's there. Ah, stop. In this case, the top has 2 terms, and the bottom has a 1. Right, that's what you should have got. So when factorials cancel, right, one factorial cancelling out with another, you tend to get this. Are we okay with that? Any questions? Okay. Next thing I'm going to show you, because it happens quite a lot, is how to deal algebraically with a fraction where the top and bottom are both fractions. Right? So imagine you had the following situation. Can you imagine this is an and this is an plus 1? It's not uncommon that you'll have to deal with this situation. And that kind of looks scary, doesn't it? Because you're going to have to try and find out what the limit of that as n tends to infinity is, and that doesn't look like it's going to be, that it's going to end well, right? So first step.
Quickly, the bottom 5 to the power of n would plus 1.
Correct, thank you. First step. Darn it in space. If you divide by a fraction, isn't it the same as multiplying by its reciprocal? Are you okay with that? If you wanted to do it kind of slowly, top guy divided by bottom guy. But isn't dividing the same as multiplying by reciprocal? So far, so good. Now, take all the pieces on the top and all the pieces on the bottom. And match them up. So put 3s above 3s and 5 above 5s and n things above n things, right? Because what we're now going to do is we are going to simplify this fraction. And the reason why I put them next to each other is you basically just simplify each piece on its own. So you look at that, and we'll see what that happens in isolation. So let's see what happens. If you had 3 to the n on the top and 3 to the n plus 1 on the bottom, you're going to have a little battle, right? Who wins, top or bottom?
Bottom.
Bottom.
What does it win by?
1.
So I won't write 3 to the 1, I'll just call it 3. Right? Would you agree that in the 5s, the top 5 wins and it wins by 1? Now, what am I going to do about this guy? You can't really cancel these, don't try. But I'm just going to write that down. So when we put the whole package together, 1 times 5 times that gets me 5n squared, and 3 times 1 times that gets me 3n squared, plus 6n, plus 3. Now, isn't that much prettier and usable than that. Isn't it relatively easy to find out what the limit of this is as n goes to infinity?
You can brute
Isn't it
force
5?
it.
Say again?
Do you use brute force?
Yeah, well, you'd end up with infinity over infinity if you said, if that's what you mean. If you divide top and bottom by n squared, you could do brute force, in which case the answer would be 5/3. But if you just plugged in infinity right now, that would be infinity over infinity, which really doesn't help us. Okay, so we're going to put all the pieces together now. We've pretty much done that in this question. And we're going to start off with a relatively, well, our only question for today, our last question for today, is n equals 1 to infinity of n over 7 to the n. So I'm going to take you through the ratio test with this very simple sequence. Don't really need to write this down, but this is mostly because of your notes. You know, if you go back and say, where the heck did this come from? Are you happy about this is who we call en, and this is who we will call en plus 1? You comfortable with that? Gives you this. So we are now going to do the limit as n tends to infinity of this guy over this. Now, these two vertical lines just mean the absolute value. And the reason we do that is we want the answer to be positive, right? Would you agree that these are positive? These are positive things. So that's going to disappear right away. And the absolute value, in this case anyway, disappears right away. And what do we get? Well, en plus 1 is that fraction over an, which is that fraction. Do you see the ugly fraction over ugly fraction situation that we kind of practiced a few moments ago? That in turn will become this guy times that guy. Now, there are quite a few lines that I'm writing down today that you might skip or combine. That's fine. But I'm trying to put every line I can think of because this is like a template for the process. Right, can you see in this question here then, don't do anything with the n's and the n squareds. Don't try and tidy them up yet. We'll sort that out later. But can I tidy up this? Yeah, a little battle going on. Would you agree 7 wins, but it's a 7 on the bottom and it wins by 1? So that gets me the limit as n tends to infinity of n plus 1 over 7n. Right, I want to know the answer to what does this look like as n goes to infinity. Couldn't I do L'Hopital and get 1/7? Couldn't I divide bottom by n and also get 1/7? Since I'm only going to do one of those two, which method do you want me to use?
L'Hopital.
Okay, so we'll stick a little L on it. It's going to be the limit as n tends to infinity. Differentiate that, you get 1. Differentiate that, you get 7. Pretty easy. And we now have the L that they're talking about. In this case, it's 1/7. And according to the ratio test, what is true if this number, this L, is less than 1? And the answer is, it converges. So we have now found out and proved that this guy converges. Right. Does the process have a bit of a flow to it? You get an a, an n plus 1, you get 2 ugly fractions, you turn that guy upside down, you get some multiplications, you do a little battle with cancelling, You get something that's nice, and then you find the limit of that nice thing. And if that number, or if the limit is a number that's less than 1, it converges. If it's bigger than 1, it diverges. And if it's equal to 1, you curse a couple of times because you spent 5 minutes and the answer is, I still don't know, right? I don't know if the series converges. I don't know yet if it diverges, which probably means I've used the wrong test, right? Maybe I should have used, I don't know, alternating series test or something else, right? Okay, say hi, everybody. Make sure you get your attendance.
Professor, what's the difference between absolutely convergent and conditionally convergent?
Oh, we haven't talked about that yet, but we'll talk about it tomorrow. The
Okay.
difference is if you take a series that converges, right? Just whatever test you use, it converges. If you turn all the numbers, all the terms into positive numbers, and it still converges, then it's called an absolutely convergent series. Now, the only time you would need to, you would use that would be probably in something like an alternating series, because in an alternating series, aren't some of the terms positive and some of them are negative, but it converges. But if you made everybody positive, it wouldn't, right? That would be a situation where you might want to know if it's absolutely, absolutely convergent or not. I believe they do those questions at the start of that section, but I want to do the ratio part first. It's more useful, and it's a nice test. And then we'll talk about, oh, there is quite a cool property. Do you know if the ratio test works and you get a convergence? The answer is it's absolutely convergent as well. You get that for free. So if the ratio test says it converges, you don't even need to check it. It is absolutely convergent for free, right? If that is us, then I'll hang about in case we have any more questions, because we may well. And if not, I will see you tomorrow. Remember, your test is Tuesday, right? And assignments are due on midnight Sunday.
Thank you.
You're welcome. Bye-bye, guys. Dwight, if you're talking, I can't hear you. Best hit the space bar.
There we go.
Right.
Is this a 2-hour or 3-hour test?
I got it in the syllabus. Tell me something. What is it?
I thought
So
it was
1 hour.
50 minutes.
50
Oh.
minutes, so 1 hour.
50 minutes.
Yeah.
Okay.
It
The
was-
final
it's just-
is 3.
Ah,
That's the difference, right?
yep, that's right.
Got it? In the syllabus?
Yep.
Better be in the syllabus. I write so much stuff in the syllabus, I forget what I've written in the syllabus. I probably have written my blood group in that syllabus. It's that big now.
No worries.
Okay, what you got now? Oh, Navy's not going to do anything nasty to you next week if it's not a secret. Are you going to be okay?
No, I should be okay. I just wanted to deconflict just in case.
Okay, gotcha. Okay, any other homework questions or related questions, any kind? Sam?
I have a quick
Douglas?
one. It's on 11.5,
Uh-huh.
number 10.
Is it a quick one to write down, or shall I have to go and look at it?
It's, yeah, I think it's quick. It's
Okay.
12 e to the power of 1 over n, all divided by n.
Oh, and there's a sigma in that, right?
Yeah, it's a sigma.
Okay, and 11.5. I'm trying to remember which tests we're under. Oh, this
So-
is comparison tests, isn't it?
Yes.
Limit comparison tests. Yes.
It's titled alternating series test. I kind of
Oh,
forgot the
well,
name.
so where's the -1 to the end?
Oh, it's there.
Oh, it's there. Okay, now
Sorry.
now that makes sense to me. Okay.
Yeah.
If it didn't have the -1 to n, it would be a limit comparison test. But
Mhm.
since it's got this -1 to the n, it is an alternating series. You know,
Yeah.
they can have a look to them, don't they? You know, certain series just look like alternating series, right? And other series look. Ratio test series, what do they look like? They tend to be fractions, and a lot of them have factorials in it, although you haven't seen one like that, or 5 to the n or n squared in it. They tend to have 2 out of those 3, or sometimes all 3 of them in a fractional form. That's kind of what they look like. Right, back to this guy. Oh, are you seeing my whiteboard?
No.
No, so I need to go back to that again. Right. Click on that one. Right, you've seen it now.
Yep.
Right, for an alternating series test, there are 2 things I need to prove. One is the limit is 0, and the other is it's decreasing. Agreed?
Yep.
Was it both pieces or one of those 2 pieces that was causing you the trouble?
It was whether it was decreasing or not. I think.
Okay.
Yeah.
Right. You could brute force this one.
Yeah.
It would be 12e to the 1 over infinity, and infinity in the bottom. Well, 1 over infinity is 0, so that's 12e to the 0. So that was 12 on the top, infinity in the bottom, and it's 0, right? It comes out really quick. So
Yep.
the real valued function is 12e to the 1 over x over x. And I need to find its derivative. I would probably write this guy in that format. And the reason I would write it in that format is that it's a product rule. Now, could I do it as a quotient rule? Sure, I could. And both would work. It's just how you want to look at it. Do you want me to do it as this product rule, or do you want me to just leave it alone and do a quotient rule? I mean, it don't matter to me.
Product rule.
Product rule, okay. Now, if you're going to do the product rule, at least the way I've written it, this is going to be the F, and this piece is going to be the G. So the product rule is F dash G plus F of G dash. If I have a choice, I always go product rule, right? If I can do it. Now, differentiate this thing. You multiply by the power and you reduce it by 1. Leave this guy alone. Plus, leave this guy alone and differentiate this guy. Well, e to the 1 over x is e to the 1 over x, but don't you also have to do times the derivative of 1 over x? Because it's a chain rule.
Yeah.
And the derivative of 1 over x is 1 over x squared. So negative 12x to negative 2, e to the 1 over x, plus, do you know this guy here, I could have written him a little differently. I could have written him like that. And the reason I want to do that is that algebraically, if I multiply these together, I can now combine them. So far, so good. And I've combined them the wrong way. There we go, 3. Are we good?
Yeah.
Now, if you pull out an e to the 1 over x as a common factor and a 12, you will be left with negative x to the negative 2 plus x to the negative 3. And I'm going to switch order and write them as fractions. So that guy is him and that guy is him. Now, imagine x is, oh, let's pick something like 10, right? You know, you can do 1, but sometimes the first 2 or 3 terms aren't helpful. So pick a number like 100 or something if you really want to emphasize it. 12 is positive. Isn't e to the power of 1/10 or 1/12 or 1/5 or 1 anything, isn't e to the power of some number like that also positive? Now, 1 over x cubed take away 1 over x squared is either going to be positive or negative. Now, when you look at it, 1 over x cubed ends up being quite a small fraction.
Yeah.
Whereas 1 over x squared is a small fraction, but not as bad as 1 over x cubed. So what you've got is a little guy, take away something that's a bit bigger. And that
Okay.
makes this
So it's
negative. So the whole thing's negative, so it's decreasing.
Okay, gotcha. Yeah, I just didn't do the product rule, so I was.
It just threw you.
Yeah, basically.
Yeah, there's some algebra skills are really helpful in all calculus, but the further up the food chain you go, they just become more and more important, right? You just have to be able to deal with weird algebraic situations and try and do what I'm calling style points. You know,
Yeah.
factoring things out is a big skill to be good at because it gets used in so many situations. It's helpful to be able to do that. Right, do we have another question or where are we right now?
Not from me.
Yeah,
You
that's all
good
I
though?
had.
Okay then, see you tomorrow, guys.
Okay, thank you.
Have a good day.
You too. Bye-bye.